This is Geometry, Semester 1 Exam Review, looking at Unit 6. So for this question number 1, we have to decide if the proportion is true or not. Well, we're looking at the properties that are true about how you can move a proportion around. And what they've done here, they've just switched the 13 and the 8. So you're still multiplying 13 and 8. So this would be true. They would call that the means of the proportion. They switched the means. Here we're looking at taking the numerator and multiplying the denominator. The property that we talk about in our notes is to take the denominator and add it to the numerator. In this case, they've taken the numerator and they're adding it to the denominator. That's going to hold up true also. You could test it if you wanted to. You could say 9 over a number. Pick a number that could represent the a value that would reduce real easily. 3 goes into 9 really easily. So the denominator's 3. Well, it's got to go in there the same way that the 3 went into the 9, so this would have to be 33. So I'm just testing to see if this theory is going to work. We take our 9, add our a value, which was 3, our b value, which was 33, so this is going to become 9/12. This is going to become 33/44. This would reduce. 3 goes into that 3/4 times. 11 goes into that 3/4 times. It worked. So if you can't remember the properties, you can always plug in numbers to test them. Here we're going to determine if the triangles are similar, and if they are, we're going to state the theorem that we used and the postulate that applies, and then a similarity statement. So here we notice that we have two lines that are parallel. Whenever you hear about parallel lines, you should always think about alternate interior angles. There's also corresponding consecutive interior and alternate exterior. Alternate interior happen a lot. You also have vertical. So that's enough to prove the triangle is congruent. We have triangle AED similar to triangle CEB, and that was by angle-angle similarity. We look here at the next one. If it's 90 on one side, then it's 90 on the other. They both have a 1 ticker. So triangle AEB is similar to triangle, I went from the 1 tick mark to the 90, so I have to go CED. Kind of tricky there. And again, I used angle-angle similarity. We look here. If this is 60, this has to be 60. If this is 50, then this has to be, let's see, that's 110, so this would have to be 70. If that's 60, this looks like 45. If that's 45, that adds up to 110, so this has to be 75. We don't have two angles the same in either one of them. Not similar. We don't have angle-angle or any of the side information. So here, this looks like a 40. This looks like a 30. So that adds up to 70. And you'd need this to be 110. Well, that matches that 110. That matches that 30. So we have angle-angle. And of course, this adds up to 140. So it needs 40 more to get to 180. The angles match. So we have triangle ABC. The order I went from was the 30, the 110, and 40. So I have to say the 30, the 110, and the 40. And again, we did that by angle, angle, similarity. On the next page and final page of our review, we have our diagram, and triangle ABC is supposed to be similar to triangle DEF. If that's happening, we're supposed to write the scale factor from triangle ABC to triangle DEF. So that's telling us what order to write the scale factor in. So we're looking for the sides that we know that are the same, that we have numbers for. The 6 goes with the X. We don't have numbers for the X and don't have the Z, so we're going to need to work with 11 and 37.4. So this is kind of peculiar with the decimal version in there. We typically would like to have a fraction that doesn't have a decimal in it. So when we look at it in this format, we're going to have to determine how this can be reduced. So one way we can get rid of that decimal, the 0.4 is not real easy to work with. So one way to do it is to multiply by 10. So I'm going to multiply by 10 to both of these to get that up to 110, and we move the decimal spot over 1. If we have our 110 and we're looking for different numbers that go into both of these, one thing we can do for sure is divide it by 2, because these are both even numbers. That would be one way to do it. 2 goes into 3 once with 1 left over, goes into that 8 times with 1 left over. I thought that was going to be breakdownable too. And actually, when we look at this again, if we divide by 11, 11 goes into 55, and 11 times 17 is 187. So, long story short, that was a tough one. Long story short, our scale factor of the small shape to the big shape is 5/17. We're going to find the value of x and z. Well, we can use our 5/17. No need to use the bigger numbers. And then our corresponding sides. That would be z for the small triangle and 30.6. It's okay to continue to use this decimal because we're just going to solve for z. So we have 5 times our 30.6. That comes out to be 153 divided by our 17. So 9 is going to be our z value. We're still going to use our 5/17, and we're going to use our other ratio, the other two sides we haven't worked with. Remember, the AC is your first and last letter, the DF is your first and last letter. That tells you that they're corresponding. 11 over 37.4. We can multiply by multiplying back and forth. Well, I'm sorry, of course. What was I supposed to use? They both have numbers. I'm not solving for anything. You need to solve for something. What letter have we not solved for yet? Haven't solved for the x. Sorry about that. Way to recognize that. So x goes on the big triangle, which goes on bottom. Be sure to put the x on bottom. It doesn't always go on top. So now we're going to get our 187. and we're going to divide that by 5. That doesn't quite go in there evenly, but our x value is going to be 37.4. Okay, the perimeter of each triangle. Well, it's a little bit easier to work with our triangle here. So we have 6 plus 11 plus 9, which adds up to be 26. Now, just for a good practice, I want to remind us that the perimeter of the triangles, or of similar triangles, have the same scale factor as the sides. So if we know that 5/17 was our scale factor, we can put 26 up there in our perimeter of the larger one on bottom. We can cross multiply and say 17 times 26 divide by our 5, and of course with all of those decimals it's not going to quite come out to be integer, but those would be units because we don't know if they're inches or centimeters. That was a little tough with the decimal and had to break that down, but nice work. Number 7, we're going to verify that triangle ABC is similar to DEF. We're going to find the scale factor. I would think that drawing a figure out would be extremely helpful. Always draw the figures when possible. We have ABC and DEF. AB is supposed to be 16, 18, and 24. DE is 40, DF is 45, and EF is 60. Well, to verify, we might be able to verify these by side, side, side. Let's see if we get the same scale factor. 16 over 40. Looks like we can reduce both of those by 8, and we get 2/5. We have the 18 over 45. Looks like those are reducible by 9, and we get 2/5. The 24 over 60. Looks like they're both reducible by 12, so we get 2/5. Triangle ABC is similar to triangle DEF by side, side, side similarity. On this one, we have triangle ABC, and we have triangle DEF. AB is supposed to be 36, 8, 40, 27, 6, and 30. And we'll do the same thing. We'll check the corresponding sides. So I typically like to use the smaller of the two triangles first. So 27 over 36. Both of those numbers are divisible by 9. Goes in there 3/4. 6 over 8, divisible by 2, 3/4. And 30 divided by 40, 3/4. So triangle ABC is similar to triangle DEF by side, side, side similarity. what is the scale factor for this dilation? So a couple of ways that we can look at this. If we would know the actual length of something, that would be good. 2, 4, 6, 8, 10. If you look closely, it looks like a 10 is written in that spot. Look closely, I think each unit is going by 2. So this looks to be 2 to the left, or actually 3 to the left and 2 down. So point A is negative 3 and 2 down. A prime is 2, 4, 6, 2, 4. So it's negative 6 and negative 4. So it looks like the image is twice as far away from our origin. And we can do that by image over original. What you need to do for scale factor is see image over original. We could take actual distances, or we could just take corresponding points. And if we take the x's of the corresponding points, the image over the original, that's going to reduce down to 2 over 1, and that is our scale factor. That was a quick, easy way to be able to verify what the scale factor was. We're going to dilate this figure with our coordinates using a scale factor of 2. So that means we're going to multiply 2 to every x and 2 to every y. So that's going to get us 2 and 2, 4 and negative 2, negative 4 and 0. So what used to have a slope of over 1 up 1 is now going to have twice that, so we're at 2, 2. What used to have a slope of over 2 down 1 is going to have that same slope a second time. What used to be to the left 2 is now going to be to the left 4. So looking at the slope to help determine works if it's a nice easy scale factor. It's not always that easy. If it was 1.5 or 3/4, that would be a challenging way to have helped calculate it, but it works. Show, last part here, show that AB and A prime B prime are parallel. So to show that AB, the slope of AB, so we take our y minus our y and our x minus our x, and we get a slope of negative 2. And we're supposed to show that it is parallel to A prime B prime. So their y values are 2 minus a negative 2 and a 4 minus a 2. Let's see, 2 minus a negative 2 and a, actually you got to go in the same order. So 2 minus 4. That gives us 4 over negative 2, which has that same slope. Same slope. Shows segments parallel. Then we're supposed to show that the scale factor is a 2. I'll do it a little bit differently this time. I'll do it by actual distances. We know our distance formula is x2 minus x1 and y2 minus y1. So we're going to find out the length of AB. our length of AB is 2 minus 1 and negative 1 minus 1. So that's going to come out to be 1 squared plus a negative 2 squared, 1 plus 4. That's the square root of 5. So now we're going to look at the length of A prime B prime. So we take our x's, 4 minus 2, and our y's, negative 2 minus 2. That gives us a 2 squared and a negative 4 squared. 4 plus 16 comes out to be 20. Well, that doesn't look like that would be twice as big. But let's think about how we would reduce 20. 20 is 4 times 5. The square root of 4 is 2, so that's 2 times 5. That's twice as big as root 5. So our scale factor is 2. You could also look at it with a calculator and say that the square root of 5 is that, and if we times it by 2, we're going to get that value. If we subtract the square root of 20, I would expect to get 0 if they're the same thing. That's one way to help verify that your answers are making sense. Good luck.